Today's presentation is a follow-up to my video Activity Coefficients in the Adsorbed Phase Part 1. In Part 1, I had examined thermodynamic non-idealities for binary mixture adsorption in sodium X zeolite. I had considered two mixtures, carbon dioxide and methane, carbon dioxide and propane. The carbon dioxide guest molecules tend to congregate around the extra framework cations, and there is an inhomogeneous distribution of guest adsorbate within the Fauger-site topology of sodium X zeolite that consists of cages of 11.5 angstrom in size. Each cage is separated from an adjacent cage by windows that are 7.4 angstrom in size. So I start today with the last slide that I had used in Part 1. I had considered configurational-bias Monte Carlo simulations for CO2 methane adsorption in sodium X zeolite at a temperature of 300 Kelvin. I had plotted the CBMC data for 50-50 mixtures with varying total fugacities F sub T in the bulk gas phase. This is for 50-50 mixture, green squares, 20-80 mixture, blue triangles, 10-90 mixture, inverted pink triangles, and the red circles are for 595 mixtures. I had used this graph to demonstrate that the Gibbs free energy, the excess Gibbs free energy divided by RT is a function not only of the mole fraction in the adsorbed phase, but of also the surface potential. That is a proxy for the pore occupancy. And in setting up, say, the Wilson model to describe the activity coefficients in the adsorbed phase, we have to introduce a correction factor indicated here, which is 1 minus exponent of minus C, a constant, times phi, which is the surface potential. This correction factor is a quantification of the pore occupancy. For vanishing pore occupancy, ln gamma of component 1, ln gamma 1 and ln gamma 2 tend to 0, and therefore the activity coefficients of both guest molecules tend to unity. For CO2 propane mixture adsorption at a temperature of 300 degree Kelvin, I had shown configurational-bias Monte Carlo simulations conducted keeping the total fugacity in the bulk phase constant at 1 megapascal and varying the composition of the bulk gas phase mixture. The excess Gibbs free energy divided by RT is a function of the mole fraction of CO2 in the adsorbed phase mixture. The message that was conveyed is that the excess Gibbs free energy for the adsorbed phase is a function not only of the composition in the adsorbed phase, x1, but also of the surface potential. And we need to set up the Wilson model, say, with 3 parameters, lambda 12, lambda 21, and the constant C. Today, I proceed further to show that it is perhaps more convenient to demonstrate the dependency of the excess Gibbs free energy on phi and x1 using 3D surface plots. The graph here on the left-hand side shows CBMC simulations for carbon dioxide and methane mixtures. 5 different campaigns were conducted. In these 4 campaigns, shown by the green squares, blue triangles, inverted pink triangles, and red circles, the composition in the bulk gas phase mixtures held constant, 50-50, 20-80, 10-90, 5-95, and the total gas phase fugacity is increased from say 1 Pascal to about 10 megapascals. The yellow diamonds are CBMC simulations for a set of conditions in which the bulk fluid phase is held constant at a fugacity of 1 megapascal, and the composition in the bulk gas phase mixture is varied for CO2 from 0.05 to 0.95. The entire set of CBMC simulations can be analyzed, and the excess Gibbs free energy determined, and the 3-parameter Wilson model can be used to quantify the deviations from thermodynamic ideality. The lines here are plotted with the set of parameters fitted by considering the entire set of simulations for the 5 campaigns as a whole. The same is performed for CO2 propane mixture adsorption in NaX zeolite. In this case, a set of 5 different simulations were carried out. In 2 sets of simulations, the bulk compositions are maintained constant, and the total fugacity is varied. And in these set of 3 CBMC simulations, the total bulk gas phase fugacity is held constant at a value, say 1 megapascal, 100 kilopascal, and this is 1 kilopascal total fugacity, and the composition in the bulk gas phase mixture is varied. Also in this case, the set of 5 CBMC simulations are analyzed simultaneously to determine the 3 Wilson parameters and the Wilson fits of the activity coefficients, and are used to determine the excess Gibbs free energy, and these are shown by the continuous solid lines here. A different way to plot these results is to use three-dimensional mesh plots. For CO2 methane mixture adsorption and sodium zeolite, I show here the 3D surface plots that is created from the three-parameter fits of the Wilson model, and the corresponding surface plot for CO2 propane mixture adsorption is shown on the right hand side. These surface plots serve to underscore the fact that the excess Gibbs free energy is a function of not only the mole fraction in the adsorb phase, but also the surface potential. For adsorption of binary mixtures of carbon dioxide and propane and cation-exchanged LTA4A zeolite, the thermodynamic non-idealities are strong and cause selectivity reversals. For example, the CBMC simulations for CO2 propane mixtures at a total fugacity of 1 megapascal is plotted here. The y-axis represents the adsorption selectivity, and the x-axis is the mole fraction of CO2 in the bulk fluid phase. We notice a selectivity reversal at a mole fraction of CO2 of approximately 0.1 in the bulk fluid mixture. This selectivity reversal also signifies the occurrence of adsorption azeotrope. Another type of selectivity reversal occurs for 1090 mixtures of CO2 and propane, in which the total fugacity is increased from, say, 1 Pascal to 10 to the 6 pascals. The data shown by the blue triangles indicate selectivity reversals here at a surface potential of approximately 26 moles per kilogram. If the mixture has a composition of 80-20, such as that indicated here by the inverted pink triangles, the selectivity reversal is not experienced. The continuous solid lines, blue, pink, and black, are Wilson model fits with three parameters, lambda 1, 2, lambda 2, 1, and C. The entire set of three CBMC simulations are analyzed together to determine the three parameters. These parameters can also be used to construct a 3D surface plot for the Gibbs excess free energy as a function of surface potential and mole fraction in the adsorb phase. We note that the surface is has a folded character and resembles a funnel shape, and this is not atypical for mixtures that experience selectivity reversals and adsorption azeotropy.